Alright, for this Mastering Physics one, we have a system of 3 blocks. The masses I have are 3 kilograms, 4 kilograms, and 5 kilograms. They're lined up in a row and they're pushed by 17 Newton force applied to the 3 kilogram block. In this case, we want to find some of the forces that exist between the objects. And so we could set up our free body diagram in F equals ma for each individual object. But what I'm going to do, and what's going to work out nicely in this case, is to treat this as a system. So we're going to have a 3 kilogram plus 4 kilogram plus 5 kilogram or 12 kilogram system. We have that 17 Newton force accelerating it to the right. We also obviously would have Fg and Fn, but we actually don't really need those in this case because there is no vertical acceleration and there's no friction, so we don't need to solve for our normal force even. So what I'm going to do is I'm going to say sum of the forces equals ma, and in this case, like I said, we are treating it as a system, so it's just that 17 Newton force equals the total mass of the system, 3 plus 4 plus 5, or 12 kilograms, times my acceleration. So I end up getting an acceleration here of 17 over 12, or 1.416 meters per second squared. Now that I have that acceleration, I can start thinking about the forces that exist on individual objects. Okay, so this part A is asking about how much force does a 4 kilogram exert on the 5 kilogram. So now I'm going to think just about the forces acting on the 5 kilogram block, and we have normal and gravity, of course. And the force that makes that block accelerate is the force of the 4 on the 5. And that's really the only force acting on it in the horizontal direction. So I can go ahead and set up my F equals ma for this one, and it's going to be the force of 4 on 5 equals the mass of that object, which is 5, times that acceleration that I just found. And that was really why we did that in the beginning. Finding that acceleration is key, because that's going to be the acceleration of each object, and that's going to help us set up our F equals ma and solve for some of these individual forces. So when I multiply that out, I get this force of the 4 on the 5 is going to be equal to 7.08 newtons. All right. So that's my answer to A. Rounding to 2 sig figs, it just becomes 7.1 newtons. And remember, it's a capital N here. Part B asks about how much force does the 4 kilogram exert on the 3 kilogram. So that's a force acting on the 3 kilogram object. Although you could set up your 4 kilogram and use your third law pairs to find this. What I'm going to do is I'm just going to set up my forces acting on the 3 kilogram. But there are other ways of doing this. So on that 3 kilogram, I have normal and I have gravity, of course. I have that 17 Newton pushing force because that's acting directly on the 3, so that is a force on the 3 kilogram. And because the 3 kilogram is pushing on the 4 kilogram here, that means the 4 kilogram is pushing back on the 3. Okay, so we have the force, the 17, and the force of the 4 back on the 3. So I can go ahead and set up my F equals ma in the x direction here. So it's going to end up being 17 minus the force of the 4 on the 3 is equal to 3 times my acceleration. And so I end up getting 17 minus that force of 4 on 3 is equal to 4.25. So the force of the 4 on the 3 is going to be 12.75 newtons. Rounding that to 2 sig figs, it just becomes 13 newtons. In case you wanted to go about it a different way and look at the forces acting on the 4 kilogram, we would have normal and gravity. The thing pushing the 4 kilogram to the right is the force of the 3 on the 4. And then because the 4 kilogram is pushing the 5 kilogram, we would also have the force of the 5 back on the 4. So we could do our F equals ma with that one. What ends up happening though is these are both third law pairs. So the force of the 4 on the 5 and the force of the 5 on the 4 are the same, and the force of the 3 on the 4 and the force of the 4 on the 3 are also the same. So we could have solved for this force. That would have also been 13 newtons, our answer to part B. Moving on to the next one here, we have a pulley system with a 2 kilogram block on a table. being pulled by a hanging 1 kilogram block. We do have friction here between the table and the 2 kilograms, so we're going to need to account for that. I'm going to start by first drawing my free body diagram. So on the 2 kilogram block, we're going to have our normal force and the force of gravity, of course. We also have that tension force, which is what pulls it to the right, and we have the force of friction going back to the left, and that 2 kilograms is going to be accelerating to the right. The 1 kilogram, we have the rope connected to it, so there's a tension force acting up, and we have the force of gravity acting on it down. I'm going to go ahead and set up my max and May for the 2 kilogram object. So in the y direction, we have Fn minus Fg, and that's going to be equal to 0 because it's not accelerating vertically. And that means that my normal force is equal to the force of gravity, which is just mg. And so my normal force is equal to 2 times 9.8, or 19.6 newtons. In the x direction, we have the force of tension minus the force of friction. That's going to be equal to the mass of the object, which is 2 times its acceleration. Notice that I made the acceleration be the positive direction, and that's why tension is the positive force there. I can substitute in for the force of friction. That's just going to be mu k times my normal force. It's equal to 2a. And I know what my mu is, it's 0.27. I know what my normal force is, so I can go ahead and substitute in those values. And so there I have my equation for the 2 kilogram. I can't quite solve it yet because I don't know Ft. All right? So that means I'm going to have to go ahead and set up my F equals ma for the 1 kilogram hanging block. And I know that that block is accelerating down. So I'm going to make that be the positive direction. So I'm actually going to say Fg minus Ft equals may. I can substitute in mg for the force of gravity minus Ft is equal to 1 times a. So I'm going to have 1 times 9.8, or just 9.8, minus Ft equals 1a. So there are my two equations. I'm going to take this one, and we're ultimately going to combine those two and solve this problem. Lots of ways to combine those two. I'm going to combine them by adding, which is the way I always do it. And when that happens, those forces of tension cancel each other out. And what I'm left with is 9.8, which is that 1 times 9.8, minus that force of friction, 0.27 times 19.6, which gives me 5.29, and that's going to be equal to 3a. I noticed that force of tension connecting it cancels out, and I also noticed that I end up with the total mass of the system, which is 3 kilograms over on that right-hand side. So I can go ahead and solve this for a, and I get that my acceleration here is 1.5 meters per second squared. Answering to 2 sig figs, it's just 1.5, and then I make sure I put in those units. If I did want to do this the systems way, I easily could do that. What would end up happening is when I'm thinking about this as a system, I have the force of friction going back on that 2 kilogram block. I, of course, have normal and gravity on the 2 kilogram, and then I have the force of gravity on the 1 kilogram. In terms of my F equals ma, that force of gravity on the 1 kilogram is going in the direction of the acceleration, so that's going to be positive. That force of friction here is going against the direction of the acceleration, so that's going to be negative. And I think that's the easiest way to think about it is, are the forces going with the acceleration or against it? We don't need to worry about our Fn or Fg2 in this particular equation, although we would need to set up the y forces acting on the 2 kilograms still to solve for Fn to ultimately solve for friction. But if we're just thinking about the F equals ma for the system, it's going to be Fg1 minus the force of friction equals 3a, which is the total mass of the system. And that is identical to the equation that I got here. This one just has the numbers filled in. But that's how you would set it up if you wanted to do it as a system instead. Okay, moving on to this next one. We have 2 blocks connected by a rope once again. One's sitting on an incline in this case. We want to know if the blocks are released from rest, which way does the block slide, and what is the acceleration. I'm going to start by identifying the forces I have here. So on the 10 kilogram, I have the force of gravity, of course. I have my normal force, and I have that force of tension going up the incline. On the 5 kilogram, I have the force of tension and the force of gravity. I'm going to break that force of gravity into its x and y components. So we're going to have Fg cosine of theta and Fg sine of theta. So I'm going to go ahead and set up my F equals ma for each object. One thing to think about is which way are these objects accelerating? And I could determine which way they're accelerating if I think about it as a system, but I'm going to show you another little shortcut that we can do, and that is I'm going to guess the direction of the acceleration. So I'm going to guess that this object's accelerating down, and this one is accelerating up that incline. And if I'm wrong, okay, none of the forces would change directions if it was accelerating the other way. So if I'm wrong, I'm going to have the right answer for my acceleration. It simply means that my acceleration was in the opposite direction. So assuming the acceleration of the 5 kilogram is down, that F equals ma is going to be Fg minus Ft equals 5a. And I can substitute in for Fg, it's just going to be mg equals 5a. So when I do that, 5 times 9.8, I get 49 minus Ft equals 5a. Setting up my x equation for the one on the incline, I'm going to have Ft minus Fg sine of 55 is my angle here, equals 10a. So Ft minus mg, making that substitution, times sine of 55 equals 10a. So I end up getting Ft minus 80.3, just mass times 9.8 times sine of 55 equals 10a. Once again, I can go ahead and combine these two equations and solve for my acceleration. So I'm going to go ahead and add these two equations, which is what I usually do. Those FTs go away, and I end up getting 49 minus 80.3, all right, canceling out the forces holding the system together, equals 15a, which is the total mass of our system. When I go ahead and solve for this, I end up getting that my acceleration is negative 2.09 meters per second squared. What that means is, it means that I guessed wrong on my acceleration. So my acceleration is not actually up the incline. It's actually down the incline for the 10 kilogram, and that means the 5 kilogram is actually accelerating up. It's still the correct answer, right? The number is still correct. However, the direction that I guessed was wrong. And I can actually see now why that's true, because this force, this mg sine of 55, pulling that 10 kilogram down the incline, is more than the force of gravity acting on the 5 kilogram, pulling it down. And so I can go ahead and insert my answer. I want it to 2 sig figs with units, and it says enter a positive if it accelerates up the ramp and a negative if it accelerates down. So I'm going to enter a negative because the 10 kilogram is accelerating down, and rounding to 2 sig figs is just going to be negative 2.1 meters per second squared. If I treat this as a system, the forces I really care about are this Fg on the 5 kilogram and the x component of the force of gravity on the 10 kilogram. Those are the forces going with or against the acceleration. And treating it as a system actually makes it a little bit easier to see which way it's going to accelerate. So we have Fg on the 5 minus Fg on the 10 times sine of theta equals our total mass, which is 15a. And we could go ahead and solve for it there. I can clearly see when I insert those numbers, 49 and the 80.3, that these actually should be flipped. And so we could go back and change the signs, knowing that it's going to accelerate down the ramp for the 10 kilogram and vertically for the 5 kilogram. Moving on to my next one, I'm going to start with my free body diagrams once again for these two blocks that are sitting on an incline. So for each of them, we're going to have a normal force. I'm going to call them Fn1 and Fn2 just to distinguish. We're also going to have a force of gravity, Fg1 and Fg2, which we of course will break into x and y components. So Fg1 cosine of 20, Fg1 sine of 20, and then same thing for Fg2, Fg2 cosine of 20, and Fg2 sine of 20. In addition to that, we have some ropes between them. So we have this rope here, and then a rope connecting block 2 to the wall. So we're going to have a force of tension pulling up on block 1, and I'm going to call it FT1 since it's from rope 1. That force of tension is also going to pull down on block 2. There's a third law pair. And then we have the force of tension from rope 2 pulling up on box 2. So there are my forces acting on each. I'm going to go ahead and set up my max and my may here. I technically only need my max for both of these actually because I don't care about any vertical forces, but never a bad idea to set up your may as well. And I'm going to start with block 1 because we're looking for this force of tension. And if I go to block 2, I have 2 forces of tension that I don't know. So for block 1, it's going to be FT1 minus FG1 sine of 20. And that's equal to 0 because our system is at rest here. So we have FT1 minus the mass of object 1, which is 5 times 9.8, just substituting in mg for that force of gravity, times sine of 20, and that's going to be equal to 0. When I go ahead and solve for FT1, I end up finding that FT1 is equal to 16.8 newtons. Rounding that to 2 sig figs, I get 17 newtons for the force of tension in rope 1. Moving on to box 2, I'm going to set up that F equals MA as well. So for that, I'm going to have FT2 going up the incline minus FT1 minus FG2 sine of 20, that x component of gravity. And that's also equal to 0 because this system is not accelerating either. FT2 is what I'm looking for. I don't know that. I do know FT1. That's going to be 16.8 newtons because it's the same force on both objects. And I can substitute in for FG2 sine theta. The mass is 3 times 9.8. That's my force of gravity times sine of 20, and that equals 0. When I go ahead and solve for FT2, I end up getting that it's equal to 26.8 newtons. Rounding it to 2 sig figs, we end up with 27 newtons. All right, moving on to this next one, we have an Atwood machine here, which is just that system of 2 masses strung over a pulley as shown. And we want to know what the mass is of this object here on the left-hand side. I'm going to start once again with my free body diagrams. So there I have them. In both cases, I have tension going up on each object and the force of gravity going down on each one. And I'm told that the 100 kilogram reaches the floor, which means it's going to accelerate down while the unknown mass accelerates up. When I go ahead and set up my F equals MA in the y direction for each one, I end up with this one being FT minus FG1 equals M times A. I can substitute in for that FG1, make it MG, but I can't do much else other than that. I really don't know too much information about that object. For the other object, I'm going to have FG2 minus FT equals 100A. I can substitute in for the force of gravity. It's just going to be 100 times 9.8, doing mg once again, equals 100A. Still don't have a lot of information for this one, so I'm going to put this on hold for a second and realize that I know the time it takes after being released from rest, and I know how far it falls, so that means I actually have enough information to set up my kinematics. So I know that I'm falling a distance of 1 meter. I'm just going to make it positive, saying down is the positive direction, which is the same thing I did over here. I know I'm starting from rest, so I have 0 initial velocity, and my time is 5.0 seconds. And so we can go ahead and solve for our acceleration here. So I'm going to use my delta x equation. My displacement is 1. That initial velocity term just goes away because I have no initial velocity. So that's equal to 1/2 times my acceleration times my time, which is 5 squared. I go ahead and I solve for my acceleration. I get that my acceleration is equal to 0.08 meters per second squared. So I can now use that in my F equals ma equations. So going back to the F equals ma on that 100 kilogram object, I'm going to end up with 980 minus ft equals 100 times that acceleration, 0.08. Okay, and so I end up getting 980 minus ft equals 8, And so my force of tension here is just going to be 972 newtons. I can use that force of tension and my acceleration over here in my F equals ma on the unknown mass. So I'm going to have 972 because it's the same force of tension minus m, and I'm going to plug in 9.8 here because we do know the value of g, and that's going to be equal to m times my acceleration, 0.08. I can add this term over to the other side, and they're like terms, so we can combine them. So I get 972 is equal to m times 9.8 plus 0.08. And then I can go ahead and solve for my mass, and I find that my mass is 98.4 kilograms. Rounded to 2 sig figs is just 98 kilograms.